Our next speaker is Dimitrios, presenting context key payload encoding.
Hello. Can everybody hear me? All right? Okay. My name is Dimitrios. I'm co-founder of Census, a Greek IT security company that builds on strong research foundations in order to provide specialized IT security services to its customers. And today I will be talking to you about context-key payload encoding. Okay, how many of you know what an IDS is? Raise your hands. Okay, most of you. And what a shell code is? Please raise your hands again. Okay, mad crowd. Okay. So, shell code are the actual instructions that the attacker uses to gain control of a system. It's actually the instructions that are going to be executed for the attacker to take control of the system. For example, in a memory corruption bug. These instructions usually provide the attacker with a command interpreter, like a Unix shell, and that's why they're called shell code. So, for those of you who don't know what an IDS system is, it's an intrusion detection system. It's a system that detects malicious activities by either examining a host environment, that's an HIDS, host-based IDS system, or the network traffic, that's an NIDS system, and that's usually part of your infrastructure as a guard in the perimeter. This presentation will focus on two topics: how to detect shell code on an NIDS system, and also how to evade detection by NIDS systems for your shell code and your penetration testing sessions. So, why detect shell code on the wire? These are 5 remote vulnerabilities that these systems have, which are very, very popular. And if you have these systems in your infrastructure, they could be liable to these attacks. So, a specially crafted packet could come into your infrastructure and gain control of your systems. For this last one, there's no known exploit that causes privilege escalation or something like that, but there is an exploit for denial of service. So, how do we detect shell code today? Let's look a bit at how shell code looks like. Your actual shell code instructions, the payload as we say, is in this part in the middle. When you have a memory corruption overflow bug, the attacker places his own return addresses at a point in memory where there used to be some addresses where the program should follow. So what he aims to do is to reconfigure the flow of the execution of the program so that it ends up at executing his own instructions in the payload. Because sometimes we don't know exactly where this exploit will land in the memory of the vulnerable application. We use what is called an obsled, which are just junk instructions. So we can point the return address to anywhere within a large obsled, and this will guide the execution towards the payload. So the 3 big schools of detecting exploits on the wire are these. The first one is signature matching. This is what most IDSs and antivirus software do. They're actually looking for parts of the shell code. So if the shell code looked like this, they will be looking for the obsled, for the actual payload, and for the return addresses. And they have a large database of known signatures, of known malware, and they're looking for that stuff on the wire. A very common case of this sort of IDS is Snort. There's also this research paper called Buttercup, which is a system which detects return addresses that they think that might be involved in some shell code execution. The problem with this approach is that it cannot detect zero-day exploits. It cannot detect stuff that it doesn't have in its signature database. So the second school is anomaly detection. In anomaly detection, what you're looking for is what is not there. You're looking for what is not part of a proper protocol. So if you're monitoring HTTP traffic, you're looking at patterns that don't look like HTTP traffic. The problem with this approach, although statistical in nature, it gives you a lot of false positives and requires training. There used to be a plugin for Snort Spade that did this. Now, the most recent attempt at detecting cell code on the wire uses static and dynamic analysis. By static analysis, we mean that we observe all payload, we observe all packets coming from the network, and we consider everything as being code. And we look in that code for stuff that look like cell code. Another analysis technique is dynamic analysis that actually blindly tries to execute all bytes coming in from the network and tries to find if at some point during this execution what is in memory looks like a cell code. The problem with this approach, of course, is that since you're doing actual execution on an emulated environment, it takes a lot of time. There's an excellent paper on this from Polychronitis from the 4th Institute of Crete. So let's see two approaches used by the virus hackers in order for them to not be able to evade detection from signature-based IDS. The first is polymorphic encoding. You take your payload, you encrypt it with a key, and during the execution of the payload, it decrypts itself and executes on the vulnerable host. The other approach is metamorphic encoding, which takes the set of instructions of the cell code and re-implements these with a set of operations that are equivalent in nature. They do the same thing, but they are different instructions. And there are ready-made tools to do this automatically for you. So in lieu of polymorphism and metamorphism, let's see how the three schools are affected. We saw that signature matching cannot be applied to polymorphic payload because the signature of the payload, because of the polymorphism, because of the encoding, will not match the one that will be found on the wire. So polymorphism is a problem there. The problem is this now. If you have the same decoder for your cell code on all of your polymorphic cell code, then that decoder could be matched by signature-based IDS. So what you can do is you can implement a metamorphic decoder for your polymorphic cell code, and that way evade the IDS detection for signature matchers. This is what the Cicada Ganai encoder does on Metasploit. Now, for anomaly detection, metamorphic encoders can produce instruction bytes that have similar statistical properties with the canonical traffic. That means that you encode it in such a way, your cell code, that it actually looks like proper HTTP traffic. There's even a paper on this that encodes payloads in a form that looks like English text. So that's how they get away from, they evade anomaly detection suites. There's the Alpha 2 encoder that does alphanumeric encoding for Metasploit. Now, what about static dynamic analysis? This stuff gets a bit trickier. So, static analysis fails to determine if a packet contains jack or polymorphic cell code because it's encrypted. The actual part of the cell code that's going to say, execute this application for me, this cell, is going to be encrypted. So, static analysis won't find it there. But dynamic analysis that uses emulation can actually find that in the memory of the decrypted cell code, because it's going to actually run the cell code and find out what it's doing actually. So, a few problems with emulation. As we said, NIDSs guard the perimeter. So, NIDSs that have emulation support emulate packets that come in from the network blindly. This emulation happens on a fake environment that is just on the perimeter. They don't have access to the actual environment where the cell code is going to be executed. Now, this minimal environment is a problem because if the cell code of the attacker depends on some part of the software of the vulnerable service that is going to receive this cell code, then this cell code will run properly on the vulnerable machine, but it won't run properly on the emulated environment of the NIDS. So that evades detection. Now, let's see what context-keyed payload encoding is. This is a cell code encoding techniques that arose from this principle of IDS evasion. The main idea is to encrypt your payload with your favorite algorithm, say Cicada Ganai, for example. At execution time, you get the decryption key of your cell code from the environment of the vulnerable host. That's the basic idea. Now, one way of doing this is with a memory-based key, as we say. You can use bytes that are found in a specific memory location of the vulnerable process and use that as your decryption key. Druid has implemented this for Metasploit. He uses a program called SMMap that takes a process and finds out when it's executing what are the static parts in memory that remain static throughout the execution of the program. Then he can use those parts as a decryption key. JDAC has written something similar for Metasploit. So if we use this type of approach for our decoding, can we actually guess the bytes that a vulnerable process will have at a specific memory region on the vulnerable host? Well, we can do this for binary package for systems that use binary packages, because systems like that don't use position-independent executables have their executable part, their code segment, in the same memory region. So you can borrow bytes from there that you know they are going to be at a certain form, because you know from the binary distribution what kind of packet you have, what kind of package you have, and what kind of version of software you have. So you can actually see for yourself what values those bytes are going to have. And you can use that as a decryption key. But of course, on systems that use pi binaries and address space layout randomization, you're going to have an issue there. The second approach is based on features of the CPU. There's a x86 instruction called CPU ID, which you can use to get information about the processor. So what you can do is you can tie your cell code to a target machine and not allow your cell code to run on another machine, for example, the machine of an investigator. Our Branko and Itzik have used the vendor ID portion of CPU ID as a cell code encryption key in their papers in Troopers. I will be extending this to include all vectors containing basic processor information, which gives us a lot richer key. This gives us a key which is of better quality. We'll XOR this information and we use it as the decryption key. So can we guess this value, the CPU ID return value, on remote hosts? Well, if you have emulated systems, then sometimes the emulated system doesn't use the real CPU of the machine. It uses an emulated CPU. So all emulated CPUs that come from the same version of the same software have the same values. Also, there are standard server models that come with standard CPUs. So you can have a database of CPU features and look up what kind of CPU you need if you understand what kind of machine you're having on the other side. So the other approach is a temporal-based key, where what you're doing, this is an approach that actually, what we're doing here is we're using a decryption key that is there at the process memory for some time, for a particular time window. This is like a time-locked cell code for Doctor Who fans. So the Hydra cell code engine uses this approach. What it does is it executes the time system call and gets a few of its high-order bits and uses that as the decryption key. In our implementation, we will be using the 16 most significant bits, which gives our cell code a time span of 18 hours. So after those 18 hours, the cell code will not be able to re-execute on another machine or whatever. Can we actually guess the value of time on a remote server? Of course we can. Okay, in most cases we can. Is it so difficult for this system call to be emulated? Of course not. You can emulate easily the system call on your IDS system, so you can catch this kind of attack easily. And it's no problem for reverse engineers, because actually brute forcing or figuring out which value of those bits is not a problem. Now, this is our new approach, which is introduced today. We're using data from metadata from the file system as the decryption key. Why? Because normally NIDSs, as they stand in the perimeter, they don't have actual access to the files of the servers they are protecting. So we can make a context key from file system metadata, like for example from the return value of the stat system call. Good candidates are the size of the file and the last modification file, and then the last modification of the file. The size of the file because you can guess it for distributions that use binary packages. If you know what version, say, of Apache the server is running, then you know what the actual the actual size of the files is going to be. Also, the last modification time for Debian-based systems is the last modification time recorded by the package maintainers. You have that as well, so we can store this and make a context key. What happens if we start a file that we later rename or delete? Well, we have the same effect as the previous example, at the temporal based, where your exploit will not only be able to execute within the time window that the actual file is there. So you also have temporal abilities there. Okay, let's see a few things about implementation details. I love this slide. Okay, design decisions. We wanted to make CKPE available to everyone, to pen testers. So we'd like to build on an open source framework, and we selected Metasploit for this. The problem with Metasploit is that it doesn't have a key generator class. So we implement our CKPE methods as new encoders, as you would have for Cicada Canine or extra additive. Context keys are generated by auxiliary applications. We give you a small utility which you can use to generate the actual key, the CPU ID or whatever. Actual payload encoder we're using is the Cicada Ganai with a 32-bit key. And the execution, and what happens if you execute that cell code in another context, it's undefined behavior. You get a segmentation for it or whatever. This is a small example of how you run the utilities we've written. Sorry. Okay, so what happens in our context key payload encoding? The encoder performs the following actions. You get the context key from the user using that utility I just said about. You generate the context key generator stub. This stub is going to be used at runtime in order to decode your payload. You encode your payload using the key that you just got from the utility, and you put two of these together and pass them to the user. And that's the cell code that the user has and it can use on a vulnerable system. To mix different stubs and encoders, we use a standard way of passing the key to the encoder. A standard way of passing the key to the encoder. So we use the EX register for this. It seems to be compatible with Metasploit encoders and doesn't mess with stack and heap layout. So this is the key generator stub for the CPU ID encoder. This is not really interesting. I will just say that it's just 15 instructions, 32 bytes overhead to your cell code. And it uses the same loop to identify your CPU ID features and collect these features as well. This is the much shorter time-based key generator code. This is the stat-based key generator code. And now let's see a demonstration. Okay. I've prepared a few payloads for you. What I'll do is I'll generate dynamically a payload which is context key encoded with a CPU ID technique. So for each payload I have three versions of it. It's the raw cell code, it's the ELF format, which is executable format, and it's the pickup format, which is it's the packet format, so we can test it with an IDS. So if for example, let's see, the raw payload uses the Metasploit payload for Linux exec, which executes a cell. We can see it here. So if I pass this to Snort, it takes some time to. Okay, what you can see here is the alerts one. That means it actually found something suspicious. So if I check my Snort alerts, it says it's actually found executable code. That is what we expect, since this is not an encoded format, it's the raw format for the payload. Okay. So let's encode this with the Cicada Ganai encoder of Metasploit and see the payload is the payload Cicada pickup. Let's see what Snort finds here. Now this is the same cell code, but in a polymorphic format. If you see up here, it says 0 alerts. It didn't find anything down there, sorry. So, how can we find this polymorphic format? We'll have to use an IDS that uses emulation. In Census, we have such an IDS, which is in research grade right now. It's in the beta form, but we will be releasing it when it's ready in open source format. And what I'm going to do is I'll use a standalone client part of this IDS to see if it can detect the cicada Ganai encoded payload. Yep, it said it traced the file and found that execv was actually called. So it found the cell code. Okay, let's see now what happens if I actually give the context keyed payload to this kind of emulating IDS. No threat was detected. It didn't manage to detect the threat. Why? This exploit was encoded with the CPU ID of this machine here, of the laptop. So if I actually run the ELF format, it's going to give me a cell. But the emulating IDS uses its own emulating CPU, and that's why in that emulated CPU, it didn't have the same CPU ID value, and so it couldn't decrypt the payload and couldn't find the cell code. So let's get back to the presentation. Best practices, how you use CKP. Okay, you use CKP to evade automated malware detection, not reverse engineers. Reverse engineers will have the time to step through the malware and find out what it's doing. But if you actually want to annoy a reverse engineer, you can use a key generator stub which uses anti-debugging code. For example, you can jump in the middle of instructions, or you can put bogus instructions there, all the usual anti-debugging techniques. You can evade signature detection using a metamorphic key generator stub, but it's even better if you actually take your normal stub and your encoded payload and use a polymorphic encoder to encapsulate all these. Also, you can use multiple CKP encoders to a specific payload, but there's no use in using the same encoder twice or more than one times. So there's a red bright code again. So we saw that modern intrusion detection systems use dynamic analysis to detect polymorphic malware. CKP prevents the malicious code from executing within the wrong context, where a wrong context could be a sandbox, an emulator, a debugger, or an IDS system. We've introduced 3 new CKP encoders for Metasploit, which we are going to make public and are referenced in this presentation. And I want to remind you that context keying is not just for shell code. You can use context keying everywhere. For example, you can have PHP code that decodes itself only if it finds specific data at a local database. How to mitigate CKP? Well, it's very hard to do this in NIDS because, as I said, because it stands in the perimeter, it doesn't have access to the context of the vulnerable servers. But you can do this very easily in HIDS systems that actually have access to the services. And there are a lot of research papers that I've referenced in our white paper that actually do this today. This is a list of references. I'll take any questions now. Thank you. Do we have a microphone? Sorry?
Why not for the IDS? So, do you want me to repeat the question? Okay, so the CPU ID and things like that, things that an attacker can guess, they can be coded in the next version of an IDS.
Exactly.
So how does your shellcode stand up for IDS 6 months from now?
For example, if you wanted to implement the CPU ID, specific CPU ID instruction, if you actually wanted to implement the CPU ID instruction, you would have to implement the CPU ID instruction of the server you are protecting. not the server where the IDS runs on. That's the problem, because the attacker wants the shellcode to run not on the IDS. He wants to run the attack on the vulnerable host. And so in your IDS system, you would have to emulate all the CPU IDs of all the machines you're protecting. Can you understand the problem? It's a configuration issue. If you're doing...
Sorry, I still think it's a finite set. How many are they? 10, 20?
CPU IDs?
Yes.
No, they're very different. It's a model of, it's a model of Intel. Okay, when I'm saying CPU ID, I'm not just saying the Intel word. I'm saying the full feature set of the CPU ID.
And how will the attacker know that?
Sorry?
How will the attacker know that?
Sorry,
How will the attacker know that in advance so that he will encrypt his payload, the shellcode with that?
as I said, in order to do that, you either have to run the actual utility on the vulnerable host, say from some other exploitable vector, or you will be able to do that by having a database of known vendor products, or if the host is running in an emulated environment, you already know that, because there are specific CPU IDs for emulated environments.
Unfortunately, we have no more time for additional questions. We'll be having a couple of drinks later, so you can
Thank you very much.
talk to Dimitris and catch up.